In this lecture, I want to talk about symmetries of regular polygons. So regular polygons. And before I start to talk about it, let me discuss a few very general notions about groups. So let's consider two groups. So G1, G2 are groups. So how can they be related? So in particular, when two groups are the same. So I'm going to discuss symmetries of polygons, and I will get some interesting groups with finite number of elements. And to talk about them, it makes sense to first discuss when I think two groups are equal and how they can be related. So the first definition is that a map F from G1 to G2 is a homomorphism morphism if for every two elements, x and y in G1, f of x times y is equal to f of x times f of y. So in particular, it's easy to deduce that f of identity is identity, f of x inverse is f of x inverse. So that's our simple corollaries of this property. So basically, this is a map, like map of sets, but it has a property that it moves product to product. And a homomorphism, so if F is a bijection as well, F is called isomorphism. So let's see what examples of homomorphisms, isomorphisms, and so on we had before. So, so here is the first example. So a couple of examples. So maybe first example might be the one we discussed in the previous lecture. So consider the group isom of R2, and then so I said that every isometry, so all isometries are classified into two types. One of them are called orientation preserving, other called orientation reversing. So let's consider a map from isom of R2 to a group S2 of symmetries of two elements, where I send all elements in isom plus, so x and isom plus will go to identity, so 1, 2, 1, 2, and x in isom minus will go to the transposition 1, 2, 2, 1. So of course one can ask, like, what two elements are reversed, and you can say that these are sort of permutations of two sides of R2. So that's of course not rigorous, but what I mean is that basically if my transformation kind of flips the upper and lower part of the plane, if I think of it as this one, it's the second type. It goes to 1, 2, to 1, and if it can be done in a way that I can do it continuously, moving the plane along itself, that's the first type. So this thing, let me call it F. So F is a homomorphism. And the reason is because actually to check that, what I need to show is that I need to show that the following sort of multiplication table holds. So if I take any element is in isom plus and compose it with any element in isom plus, I will get an element in isom plus. If I take any element in isom plus and compose it with any element in isom minus, I will get isom minus. Similarly, if I compose it in the other order. And finally, if I compose two elements which are orientation reversing, I will get something orientation preserving. And this is indeed the case because basically last time we discussed these are compositions of 2k symmetries. And these are compositions of 2k plus 1 symmetries. And then, of course, if I compose even number of symmetries with even number of symmetries, I get even number of symmetries. Even number of symmetries with odd number of symmetries, I will get odd number of symmetries. Odd number with odd number, I get even number of symmetries. So basically, we proved it last time. So that's the first example of a homomorphism. And now let me consider another example of a homomorphism. So second example is as follows. So consider as G1 will be the group of symmetries of a triangle, of a regular triangle. Let me call it T. This is a regular triangle. And G2 will be a group of symmetries with 3 elements. So here is a picture. So let's draw a picture. So we have a regular triangle, ABC, with a center O. And then I have a group of symmetries of T, and I can even write down all its elements. I can write down just the whole list. So I have identity, and then I can rotate it. So there is this rotation with a center O by the angle 2 pi over 3. I have rotation with the center O and the angle 4 pi over 3. And then 3 symmetries. Symmetry with respect to line OA, symmetry with respect to line OB, symmetry with respect to line OC. And then S3 also has this elements which I will, let me write them down, sort of related to that. So I have an identity, I have a pair of cycles of size 3 and triple of cycles of size 2. The statement is that these two groups are isomorphic, meaning there exists a bijection, which is also a homomorphism. So let's consider F a map from G1 to G2 from sim of T to S3. So S3 will be permutations of the set of 3 vertices A, B, C. So of course, when I have a set and I look at permutations, it doesn't matter much which set I permute. Usually I denote it by 1, 2, 3, like here, but I want to denote the elements of the set by A, B, and C. And then I can send F to a permutation, sending A to F of A, B to F of B, C to F of C. So this permutation is a permutation of vertices. So I will formulate in general for arbitrary or regular polygon a similar fact in a moment, but what I'm using here is that an isometry, so F inside sim T sends vertices of T to vertices of T. So a priori it's not obvious, but actually that's really easy to see that a permutation which sends a triangle to itself has to send vertices to vertices. So I will discuss it in a minute, but if I assume that, then one can easily see that this gives a permutation of 3 elements which are vertices. And for instance, I can compute it here. So for instance, this will go, so it's rotation by 2 pi over 3 here. A will go to C, C to B, B to A. A will go to C, C to B, B to A. And here, A will go to B, B to C, C to A. Symmetry OA will go to, so when I reflect with respect to OA, B and C are exchanged, A goes to A, B, C go to C, B. When I make a reflection with respect to B, A and C are exchanged, B goes to B, and here obviously A and B are exchanged. C goes to C, and here A goes to A, B to B, C to C. So this F sends product to product, and that's obvious because basically if you compose F and G two isometries, of course these permutations will be composed because just this is F restricted to the set of vertices. And so F is a homomorphism. So F is a homomorphism. Homomorphism, that's obvious. And F is a bijection. That means there are 6 elements here, 6 elements there. And actually, the simplest way to see it is that we know that if 2 elements in F go to the same element here, it means they will send ABC to the same points. But we know that a transformation fixing sets sending an isometry is uniquely defined by its action on 3 distinct points, not on the same line. And so this has to be an injection, but sets are finite with the same number of elements, so it's a bijection. So this is an example of an isomorphism. So then F is an isomorphism. And so we say that groups, if there exists an isomorphism, we say that groups are isomorphic. So in a sense, we think of them as the same. And so the notation is that these 2 groups are isomorphic, and this is a notation. Okay, so this is a very important example of symmetries of a triangle. And now I want to discuss in a little more detail symmetries of arbitrary regular polygons. Okay, let's talk about symmetries of regular polygons. So, so let's consider a regular polygon. So let Pn be a regular n-gon with vertices a1 up to an. So I can draw it, and I will draw maybe 2 pictures. So it's a 5-gon, and that's a regular, sorry, 6-gon and 5-gon. So that's P6, and that's P5, and you'll see why. So the vertices are A1, A2, A3, A4, A5, A6, and here A1, A2, A3, A4, A5. So first little observation, maybe lemma, is that a point P, or point X, in R2 is a vertex of Pn if and only if there exists a line L such that if I intersect L with Pn, I will get X. So by Pn, by the way, I mean all the kind of a closed figure where I take all points inside and vertices and sides and so on. So here is a picture. So there exists a line. So a point is a vertex if there exists a line which intersects a polygon only in one point. And the proof is more or less obvious. So if you take any point on the side, every line will continue like a little segment going inside the polygon. If you take a point inside, every line contains a little interval. If you take a point outside, the polygon will not contain the point at all. So that's a little Euclidean geometry argument I admit, really easy to see. And so an isometry F inside sim of Pn sends vertices to vertices. To vertices. And so why? Because it sends lines to lines. Points in the polygon to points in polygon. And of course it's a bijection, so it sends intersection to intersection. And so if you take a point which is characterized by the fact that there exists a line which intersects exactly in this point with the polygon, then it will go to a point which satisfies the same condition. And so vertices go to vertices. Also, F is a bijection, so distinct vertices go to distinct vertices. So then F inside sim of Pn defines a permutation sigma F inside Sn, where this is a permutations of vertices A1 up to An, which I will just identify with labels, sort of. Okay, so sigma F composed with sigma G is equal to sigma F composed with G, just because we do two isometries one after the other, and then we look at how the first one permutes the vertices and how the second one. Of course, the composition is exactly how the composition permutes the vertices. That's completely obvious. So we get a homomorphism. From the group of symmetries of Pn to Sn. And let me call it sigma. So sigma sends F to sigma F. And it's really easy to see sigma is, of course, injective. And the reason is because, as we argued with the triangle, if we know that two isometries do the same permutation with vertices, there are 3 points not on the same line, which go to the same points, and so the corresponding isometries are equal. So it means that there is this map which is injective. So basically, if we just identify symmetries we can identify symmetries of Pn with corresponding permutations of vertices. So let's, for instance, consider a case of a square. So that's P4. And then there are like 1, 2, 3, 4 vertices, and one can write down all permutations. So we know that vertices go to vertices, and moreover, it's easier to see that consequent vertices have to go to consequent vertices, opposite vertices have to go to opposite vertices, and so actually there are the following 8 permutations. Identity, cycle 1, 2, 3, 4, corresponding to a rotation by 2 pi over 4, and then there is this permutation which exchanges 1, 3 to 4, which is one can say a central symmetry, center O, and finally there is another cycle 1, 4, 3, 2, which is a rotation by 3 pi over 4. 2 pi over 4, 4 pi over 6 pi over 4. And these are 4 rotations. And then there are several reflections. So there is a reflection with respect to this axis of symmetry, this axis of symmetry, this, and this. And so basically these are permutations 1, 4, 1, 3, 2, 4, and these are the two where they fix a pair of vertices, and then there are 2 others, a product 1, 2, 3, 4, and a product 2, 3, 1, 4. So these 8 permutations form a subgroup of S4, and these are exactly the isometries I can get, permutations which I can get by looking at isometries of a square. So in general, one can easily conclude that the orders of this number of elements in sim Pn just equals to 2n. And n of them are, so n rotations by 0, 2 pi over n, 4 pi over n, and so on, and n symmetries. And interesting fact is that n-symmetries are kind of a little distinct. So in the case of an even polygon, there are two types of symmetries. So for hexagons, there are 3 symmetries with respect to lines passing through a pair of opposite vertices, and 3 symmetries with respect to lines which pass through the mid of opposite sides. And for an odd polygon, all symmetries are basically just symmetries through a vertex and the opposite mid of the opposite side. So these are the 5 symmetries. Yeah. So in the next lecture, I'm going to discuss this n rotations in more detail. So the group formed by rotations preserving a regular polygon is a very important group called a cyclic group.